camera. Okay, my watch says it's 6:05. So welcome everyone to this virtual lecture. I'm not actually expecting everything's always going to go smoothly because this is the first time we've done this, but we'll see what happens. Like in the middle of all that, I get pop-up messages from annoying bits of software. Okay, so last week we talked about relational databases, and this week we're going to do a bit of a revision of the end of last week, and we're also going then to move on to relational algebra and SQL queries. Before I do that, there's an announcement that there's been some confusion between what's written in a unit of study and what was in the guides for students, but we've come to an agreement that there's a slight adjustment on the way the course is being assessed. The last two assignments will be worth slightly more than they were before, and the exam will be worth slightly less. So that's the only change. Week 9 assignment is up from 10% to 15%, as is week 12, and the exam's down from 60% to 50%. Okay. So last week and the week before, we started talking about enterprise relationship modelling, ER modelling, and there is the typical one we'll be using for this quick bit of revision. Most of the links between the entities and relationships are just ordinary, unconstrained ones, and there are a few constrained ones, like from unit of study to teach is constrained, and from lecturer to supervise is also constrained. This is someone hasn't got the microphone on. You can see the background chatting from that. On slide 5, that's a relational model of the same system. There are fundamental entities in the system, and it's notable that, go back, in many ways the relational model is simpler than the ER diagram. They both capture the same information, but I find the actual database schema simpler and more comprehensible because I'm used to dealing with them. So now we've got some relationships represented as those arrows, meaning this links to that as a foreign key relationship. So enrolled goes to the unit of study via sharing a value for the EOS code. So a particular enrolled record is linked to a particular unit of study record by sharing exactly the same value for EOS code. And then as we add more relationships, there's lecturer goes to lecturer, and that would be via EMP-ID. I'll come back to why that's called that. And we've got one of these nasty recursive relationships between lecturer and lecturer because some lecturers report to other lecturers. So we've got a circular relationship there. And if I go back to here, you see we've got two relationships between lecturer and supervisor. We've got one called manager and one called supervisor. And every lecturer has to have a supervised relationship with some other lecturer. And of course, the question that comes up there is, what happens when you're the Vice Chancellor or Chancellor where do you go at the top of the tree? And then the answer would be either you supervise yourself or you have a null supervisor. But that's just a question of how you want to arrange that in the database. Relational models is built up of relations, which are tables, and we have a schema for each of these relations. That's just the name of the table and the names and types of all its attributes. Those attributes are also called columns and fields. Doesn't matter what word you use. And the tables consist of rows, sometimes called records, and often called tuples. That's just the word we use. So it's derived from multiple. So tuples. So you've got a table with 3 rows in it, 3 tuples in it, called student. And typically we'll be very rough in our terminology, and we won't talk about the relation, meaning the table, it's a relation instance. We'll just talk about relations because that's what we're interested in. Relations are a mathematical concept. Relational databases have tables which are not quite identical to mathematical relations, but they're very similar. And the main difference is that in a mathematical relation, because it's based on sets and the mathematical concept of a set, you can't have duplicates. Every row has to be distinct. You can't have 2 rows with exactly the same set of values for all their fields. Whereas database tables can have duplicate rows. Sometimes you may not want to have them, so if you allow in duplicate rows, that might actually be a problem. And lots of bits of database technology assume you don't have them, assume that each row is distinct in some way, but it's perfectly okay to have duplicates. And we'll often get duplicates coming out as the result of queries. Then we'll do something to get rid of the duplicates as part of our query processing. So the core entities probably won't have duplicates in them, and we'll make sure they don't. But when we're creating more tables as a result of queries, then they may well have them all. But that's something we need to be aware of. But you wouldn't normally have duplicate rows in the entities that you're creating as part of your database. Keys. Every relation can have keys. A key is simply something that can be used to uniquely distinguish an individual row in a table from every other row. You can have multiple attributes or sets of attributes which serve to distinguish one row from another, and they're called candidate keys. We'll typically pick on one of those candidate keys and give it immense status and call it a primary key. But we're just calling it primary key for convenience because other bits of the database technology like having a primary key around. It makes life easier, or we don't have to, it lets us be lazier, which is always a good thing. So for the student table, student ID is one of these synthetic keys whose only purpose in life is to be a candidate key for a student record. So it would definitely be a candidate key. We could combine student ID with the student name, and that would certainly be distinct as well, but it would only be distinct because the student ID was distinct. So it's potentially a key, but it's not really one. So we're saying yes to the first question there, no to the second. And for enroll, can student ID be a candidate key? No, because we can probably enroll in lots of courses, so there'd be lots of records for the same student. Could student ID and unit code be a candidate key? Yes, as long as you're not allowed to repeat a unit, as the note at the bottom says. And could student ID unit code semester be a candidate key? No if you're not allowed to repeat, yes if you are allowed to repeat. So there are answers. You'll study later. Now, the other thing we did last week, which I thought the slides needed some improvement on, so the slides in this part of last week's lecture have been revised slightly just to try to make them a bit clearer. After I wrote this revision, I thought, the original slides could do a bit of work as well. So there's no real change in the content. I've just changed some words to try to make them a little bit clearer. So when you're doing your revision, you can go back and look at the revised version of last week's lectures. So here we've got two entities, A and B, and a relation R. And we're often interested in the degree of a relationship. A and B in one-to-one. So every A is always tied to a B and every B is always tied to an A. So one-to-one relationships. And what we would typically do when we're going from ER model to relational model, if we have a one-to-one relationship, we will simply merge the two relations. We'll take A and B and we'll concatenate them. That's all we need to do. I'm introducing this arrow notation, which I think I used last week as well. This is a pretty common notation to use if you're skipping ER modelling and just going straight into relations. It says A and B are related, and the thing in the middle is the relationship, and the degree is indicated by the arrows. 1 and 1. Next time will be 1 and 2. So 1 is a one relation and 2 arrows is a many. So here is A and B. We just take all the fields from A and all the fields from B and join them together and we get a new relation AB. If you have a one-to-many relationship where one thing here is related to many things here, so one A is related to many Bs, for example, each department has multiple employees, then that's a one-to-many relationship. And the way we handle that is take the key, the A candidate key or the primary key of the relation on the one side of it and insert that as a foreign key attribute into the relation on the other side. So we've got A and B again, B's primary key is B, so we add B as a foreign key attribute to A. There's an example with department and employee. Department has a key of department ID, so we'll add department ID as a foreign key attribute to employee. And then the full-blown, we have really no constraints, is a many-to-many relationship where any number of these can be associated with any number of those with double-headed arrows on both ends. So department to employee, that says an employee can have can work for many departments and department can work for many employees. And we implement that by creating a new relationship. I'll call it a relationship relation, which is composed primarily of the foreign key attributes from both the left and right hand entities. So we've got A and B, the keys A1 and B1 will create a new entity relationship, ABR, whose primary attributes are the key from A and the key from B, and can other attributes as well. So we call with department and employee, there's department, employee, and our worksin is now a relationship in its own right, and it consists of just the department ID and the employee ID. And that's basically how you do it. Constraints. In the ER world, we took those lines, like the one that's circled in red up there, and we played with them. We could turn them into an arrow. We could make them a thick line, bold it, or we could make it into a bold arrow. They're the types of things we could do to change the constraints on that line. In the relational world, we can make a given attribute, possibly a foreign key attribute. We can allow nulls for that value, or we can say it may not have a null value. And we can also declare an attribute or a set of attributes as a candidate key by declaring that they are unique, because no two rows may have the same values for those key attributes. And we explicitly can declare foreign keys. So when we say this attribute is a foreign key, and we say it's a foreign key for some other relation, and the database knows about that, and by default, when we just say that, it will go and pick up the primary key of the other relation. And referential integrity will say that when we say employee A works for department B, it will check that B is a valid department ID. So referential integrity takes care of that for us. Now, back onto the ER fancy lines. A single non-bolded arrow means at most once. Now, the next two columns need a bit of explaining. The first one is if we are implementing a one-to-many relationship, and we're doing that by putting the foreign key in the appropriate place. So if we're doing department and employee, we put the department ID in as a foreign key in the employee record. So that's a one-to-many. And that's our normal standard way of doing relationship modeling. The more general and rarer way of doing a relationship is when we're implementing end-to-end. In this case, we have a separate relation which is embodying that relationship. If we want to impose a at most once relationship we picked up from our model and we want to impose it in the relational model, we can do that in a one-to-many model by declaring that the foreign key can be null. And because it's at most once, the foreign key points off somewhere, and we say, well, it has to point somewhere, and it can point to nowhere. So at most once there's 0 or 1. So the 0 is taken care of by being a null. And the once is taken by that this is just an attribute, and attributes have to be single valued. When we talked about relations, one of the first things we did going from entities relations was saying we're not allowed to have multi-valued attributes. So every attribute only has a single value, so that takes care of the once part of it. So single arrow at most once is we say it can be null, and because it's an attribute, then there can only be one of them. I'll skip the bold for a second and come back to it. Exactly once, it's the same thing. We've got 1 because it's an attribute, and by saying it can't be null, then that means that there has to be a value there. So we get exactly once by having our foreign key declared to be not null. The middle one, at least once, just has no meaning. We can't map that because in a 1 to m implemented by using a foreign key, we can't have more than one value for the foreign key because we did it as a foreign key. So because we've chosen this mapping, we can't have more than one value, so we can't map the single bold non-arrow if we're doing a foreign key implementation relationship. When we go to many-to-many, we now have a separate relation. We do at most once by checking that the appropriate foreign key in the relation is unique. So we've got end-to-end between employee and department, then it works in, then by saying the employee ID is unique, it says I can't have more than one record in works in with the same employee ID. So that means once, and it may or may not appear in there, so it can be 0 as well. And the other two, we can't implement just by adding attributes to the entities or their attributes. We would have to go and write code or queries to check that all the time. I could do things like do a count of the number of employees and a count of the number of distinct employee numbers in works in and make sure they are the same. That would do, but it's not possible just by adding some attributes. Okay, that's the end of the revision. If you go back and look at the revised version of last week's slides, you'll see I've put some of that material back in there, try to make that a bit clearer, because last week's slides just sort of glossed over the implementation of the bold and what you do about many-to-many relationships there. So I thought I'd better just go through all the possible combinations there. Okay, today, queries. Going to do relational algebra to start with, and then we're going to go from there to its close cousin, SQL queries. Relational algebra is an algebra in the mathematical sense, and it's an algebra over relations, and it looks a bit mathematical. And SQL were the people who did SQL tried to take the ideas from relational algebra and just make it more amenable so that ordinary people could use it. There's the example we'll be using. You might want to go back to that when you're looking through the slides later on. But that's the example we'll be using. Straightforward student, unit of study, via enrolled, and enrolled is an actual relationship in its own right. Relational algebra. So I'll ask you to give you these three tables and just think about how you would, if I asked you to give me the names, the titles of all units of study that were worth exactly 6 credit points, how would you do that? Pause, think. So I suppose I'd go to the unit of study and I'd go look through it sequentially and say, oh, that one's got 6 points. That one, those three have 6 points. So I would take that table and I would just extract from that table those top 3 rows. That gives me all the units of study worth 6 points. And then I only want the title. So then I would throw away the OS column and the points column and just return a little table which is relational DBMS, data mining, and IT project management. That's what I'd do if I was doing it manually. That would be my result. And that's basically what we're going to do in relational algebra. The 2 operations I did were selecting out of the unit of study just those rows that were worth 6 points, and then projecting from that just that particular column. So I did 2 operations, a selection and a projection. So what we're going to do in relational algebra is do a selection. That's that little curly thing, a sigma. Sigma is Greek letter S, so it's an S in Greek, and the people who did it were mathematical, so they like Greek letters. So that's our selection operation, our sigma, and we're going to follow that by a pi. P is the Greek for P, so that's our projection operation, and that just takes those columns. And that's beginnings of relational algebra, 2 relational algebra operations, sigma and pi. And there is the actual relational algebra expression, which if you ran that on that table will give you the result you want. So we're taking the selection operator with a criteria of points equals 6, applying that to the unit of study, taking the set that came out of that, and doing a projection operation, just taking the title. It's pretty straightforward. So, array. It works on relations. Relations are sets, so it's very set-based. And it's very functional. If any of you done functional programming, it's functional. The operator takes a set, does something to it, and returns a set. And then that can then be used as the input into another operator. So there we've got unit of study is our initial set, that gets worked on by the selection operator, that returns a set, that gets worked on by the pi operator. Oh, pretty straightforward. You ignore the Greek. The way down buried underneath SQL is relational algebra. And the reason we're covering relational algebra here is because in some ways it's the underpinning for SQL. I find it often easier, if I'm doing something complex in SQL, to think, what's this really mean? And I think about what's it really mean in terms of some of these relational algebra operations. So SQL is really exactly the same set-based concepts, but with a more amenable language. It's not mathematical, it's more English-like. And we've had this picture before. When you put in a SQL query, the first thing that happens is it gets attacked by the SQL query parser, and that is how to declare it in. We translate that effectively into a relational algebra expression. We don't really, we turn it into the data structure, which is equivalent to the relational algebra expression. But you might as well say it's a relational algebra expression. That gets fed into a thing we'll be talking about in a later lecture, the query optimizer, which tries to work out how I can take that algebraic expression and manipulate it to execute more efficiently. That gives us a query plan, and the query plan then gets fed into the engine, which then takes all the tables, does the stuff, and gives you the result. This picture we've been referring to all through the course of what's an RDBMS look like. There we get our SQL commands coming in, and that bit we just did on the previous slide is those top 4 green boxes: the parser, the optimizer, and the execution engine. There we go. Aren't Bill's wonderful? So, array operations. Each operator takes 1 or 2 relations as input and gives you a new relation as a result, and you can nest these. We've got nesting there of the sigma inside the pi. So the way you'll make long complicated things is just by nesting. And there are some other conjunction operators we'll come across. So we can do expressions. There are operators that, primary operators we've seen before, sigma and pi, want to take a relation and give you a smaller relation, either fewer columns or fewer rows. There are a set of operators that take relations and join them together. They are cross product and its close cousin, join. Cross product, so join is really a cross product followed by a selection. But we'll use those a lot. And then because we're dealing in a set-based world, we have all the normal set operations available: union, intersection, and difference. And there's one last operator here, which is rename, row, and that's just to be nice to us because we sometimes want to rename something. We've got the same attribute in 2 relations, and we want to keep them both, and we want to rename one of them, so we can just rename it on the fly in the middle of an expression. So that's just for convenience. So projection. We just we got some type of projection list, an expression that says, here are the columns I want. I take those columns and throw away the rest. And if there are any duplicates resulting from that, I throw away the duplicate rows, because these things are sets and we can't have duplicates in sets. So student had lots of attributes before. If I just do a projection for name and country, I simply pick up a new table, which has just got name and country, and there's projection of just country. And this temporary table expression that we got back contains just the attributes that were in our projection list. So name and country here, country here. Selection does the opposite. It keeps rows and keeps all the columns and throws away some of the rows. So if we just wanted, from our previous table, all the students whose country was AUS, that expression will do that, and that would be the result. Same schema as we started with. If we want to do a selection but throw away some of the columns, we then have to take that expression, the result of that expression, and drop it in to a projection operation. That's straightforward. The selection condition is just a Boolean expression, and like everyone will be used to, normal operators with ands and ors, etc. So there's one. So here we say select students whose gender is an M and whose country is AUS. I think I've said that these things can be nested. They'd be useless if you couldn't nest them. Okay, cross product, the first of the more interesting ones. This is, there'll be a note on the slide coming up. I would normally call this a Cartesian product, because that's what I normally call them. And it just takes, we've got R cross S. We take every tuple in R and add to it the value of every tuple in S. So we'd have, was with the example, we've got R with two columns A and B, and S with C, D, and E, and we'll take the first row of R, which is alpha and 1, and we'll take alpha and 1 and combine it with all 4 rows in S. So there are our first 4 rows in the cross product, and then we'll do the same with the second one, beta and 2, combine with all 4 of those. There are all 4 of those. And this is one of the reasons why we might have that rename operation is, of course, when we do this cross product, there's no reason why that couldn't have an A as well. And we don't want to call A here in our cross product, so we might want to rename it on the fly. We could do that if we want to. If either R or S is empty, then the cross product is also empty, because there's nothing to join. If S was empty, there's nothing to join the rows of R onto, so R cross S would also be empty. It's normally called a Cartesian product, as far as I'm concerned, because that's what I always call it. And at the very heart of the join operation, and really at the very heart of anything other than the simplest SQL query, are cross products, Cartesian products. As you saw, R times S automatically gives you the size of R times the size of S number of rows, and that's not necessarily what you want. Join says, why don't you do a cross product and then do a selection on the cross product? So we'll write it as R join symbol theta, and theta is our expression here, the joining expression. And that's exactly the same as a cross product fed into a selection. So we don't really need the conditional join operator for completeness, because it's actually just the composition of a cross product and a selection. So here's an example: student conditional join with the student first name equals lecturer last name, and student ID is less than lecturer employee ID. Sounds like a pretty crazy condition to me, but that's okay. So we do the cross product and we go and look at each one of those and say, does it meet this criterion? The implementation for conditional join is the cross product followed by the selection. This is sometimes called a theta join because it's got an arbitrary selection expression of theta. There's a special case here called an equijoin, where the theta only contains equalities. So this isn't an equijoin because it's got a less than there, but if we only had equalities in there, then it would be an equijoin. Equijoins are very common, and particularly they're the basis of a thing called a natural join. So if we go back and look at the symbols here, there's our cross product is the X, the conditional join is the bow tie with the theta, the natural join is just the bow tie without the theta, because the theta is equality on all the fields, all the attribute names that are in common. So we've got enrolled and unit of study, they both share the US code field attribute. So if we were to do a natural join between enrolled and unit of study, we would say, oh, they've both got unit of study code, so we'll join them together on that. So I'll get 1001, comp 5138, relational databases, 6 points. And that's our first row. So we'll just join them together naturally on that. Result scheme is similar to cross product, but we don't keep multiples of them. So we don't have 2 US codes in here because we keep the first one mechanical. Okay, an exercise. I can't really go and ask the class in general for the answer to this because it'll just be too clunky. And questions you're asking on the fly, I can't really look at them while I'm doing it, but any questions at the end you can send to me on Canvas and I'll answer them on the fly. It's a bit hard focusing on the slides and keeping track of a little window down here which has got questions in it. So there's R, A, B, C, D and S, A, C, E. Equijoin of that, well, A and C are in common. So you'd think then that the schema of R and S would be that, and that. There we go. I'm glad I was right there. And A, B, C, D, E, there's nothing in common. So I just get it becomes a Cartesian product. And A and B, I get A and B. The set operations, all the ones you know and love. Union, where we take two things and go blong on them. We take everything in both of them. Intersection, we take only the things that are in common. Set difference, we take one set and take everything out, which is in the other. We've got more bills there. There we go. So R plus S, only the things in common, and R minus S. To do this, R and S must have compatible schemas because we're treating them as being identically shaped. So we've got two relations here, student and postgrad, and I want to use a set operation to return all students who are not postgrads, or they've got SID in common, so that's good. So the schemas are compatible. So if I take the projection of student, which is just the student ID, so now I've just got this column here as a table in its own right, and subtract from that the postgrad table, then I'll keep that one, and that one. 1001, 1002, and 1006. Okay. Rename operation, just as a rename, it just takes the expression E and calls it X, and when I do that, I can relabel the columns as well. And it just modifies the schema of the expression that we're returning. So, for example, that could be some complex expression, but I want to rename things on the fly. We'll use that quite often when we're doing SQL queries. So there's an example. We've got unit of study, and we want to relabel, get a new unit of study table where we're taking points and calling it credits for some reason. So we'll get unit of study, we'll get a new table called UOS with attributes UCode rather than UOS code. Title is the same, and credits rather than points. Not a particularly great example here, but you'll see how we use it very frequently when we get to SQL. This is something you probably want to revise later. This is a nice one-page summary of those relational algebra operations. As I said on the way through, not all of those operations I used are actually fundamental. Some of them are just there for convenience and could be derived from the fundamental ones. So join, for example, is really the Cartesian product followed by a selection. And when I get to doing some SQL queries, I need to think about that, because in the SQL syntax, there's a bit which is basically just a cross product, and there's another bit which is basically just a selection. SQL maps pretty much one-on-one with relational algebra. So RDBS tables allow duplicates. There have been generalizations to the relational algebra operation we're going to talk about here to handle that problem. Okay. Because this is set-based and it's all expressional, I can commute things around. I can take things and move, nest this inside that, or move that from being inside to being outside, and the result is logically identical. There are many ways of expressing exactly the same query. They're all equally correct. When we go and look in week 12, when we talk about query optimization, we'll find that not all of them are the same execution cost. Some will be much more expensive than others. And one of the, I said we take SQL queries and we turn them into something which is effectively a relational algebra expression. That gives us an expression tree, and then we can start manipulating that tree. We can move things around and optimize it based on our understanding of what's in the tree and what's in the database, the costs. Okay, some references for that. And it's now 10 minutes to. I think that's an ideal place for a short break. I'll have a quick look through some of those comments if I can, and I'll talk about some of those when we get back. So let's get back. It's just before 10 to, and we'll start again at 7 o'clock. And then we'll do the SQL part of this. It's a really nice breakpoint. Okay, I'll be talking again just at 8 o'clock. Sorry, 7 o'clock, an hour out. I'll be talking again at 7 o'clock. Just in case any of you are wondering what one of those photographs in the background is, snow gummits and snow daisies. It'll be part of next week's quiz. I should scan the photographs and put them on canvas. There's another one that I can get without the reflection. That's another snow gum. See the way they're all gnarled and multi-stemmed. They're probably hundreds of years old, because you only get a fire through there every few hundred years. And these are old gnarled trees. I have no idea how old they are. But they're fantastic trees. You get their scientific name is something like the Eucalyptus nififila, which means snow lover, which is much nicer than their previous name, which meant poor flower. They're a lovely tree. And luckily those ones didn't get burnt in the last big fire down there, either this year or 20 years ago, almost 20 years ago. Perhaps I'll scan some photos and put them up on canvas for you to admire. You can't see the map of Genola Cave next to it though, because it's out of sight of the camera. Latin, it says. Scientific names start up being sort of Greek and Latin. Yeah, they just are. And even if they're not, I've got a name on a fungal paper describing a root fungus, Australian root fungus that helps plants survive. And my colleague who basically wrote the paper, he studied that particular fungus as part of his PhD, and 15 years later he got round to writing the paper describing it. Scientific names have a genus name and a specific name. So this particular thing is Gamarada debrolocki, and Gamarada is an Aboriginal word that he chose because it's the first fungus in that genus. And then debrolocki is named after the woman in our building who cleans the scientific glassware, because he thought that she's often underappreciated. So he named this particular organism after her. So you get a fair bit of flexibility. It's not considered nice to name it after yourself. Okay, almost time. I'm waiting for the punchline. There was a 19th century, early 20th century scientist, Haldane, JBS Haldane, and very famous English scientist of his day. And there's a story about him meeting up with the bishop, and the bishop says, "Oh, your studies of the natural world, Mr. Haldane, Professor Haldane, what do they tell you about the mind of God?" And Haldane looked at him and said, "He's inordinately fond of beetles, because there are more species of beetles than there are species of anything else. So God is particularly fascinated with beetles." Okay, let's assume everyone's back, refreshed, and we'll talk about SQL. You are probably unlikely to ever come across relational algebra in your working life, unless you happen to be a computer science academic, but you very likely come across SQL. And the two are deeply wedded. Okay, I can get this to respond to me. Here we go. SQL, normally pronounced SQL, which is a bit odd. So relational algebra is this very mathematically based and founded thing. It's pretty cryptic. You wouldn't expect your average computer science type person, non-computer scientist, academic to understand it, certainly not your average programmer. And we have to work with average programmers because they're average. It's got lots of Greek letters in it and other funny symbols. So no one uses it. We do use SQL, and very similar. They're both declarative languages. They're both set-based declarative languages that say, what data do we want to retrieve from the system? How do we want it organized, etc.? Not how should the system do it. These are not procedural languages where you say, write a for loop and pick up the next one, and look at field this, and if that, do this. None of that. You just say, here is something that defines what I want, and you take care of working out how to get it most effectively. So SQL is often pronounced SQL because we like pronouncing acronyms, which is a bit ironic as it's actually based on a language called SQL, simple structured English query language, and that was the query language introduced for the first relational database system, System R, which was done by IBM down in Southern California. And when we take a SQL query, drop it into the parser, what we pop out of the parser is effectively an expression tree. Just like all the other parsers we have, we take something and we turn it into some type of expression tree, and that expression tree has an even stronger relationship to relational algebra expressions. Okay, SQL is standardized. It's been through any number of standardizations, revisions. I doubt there are any implementations out there which are purely standards compliant. That's both for historical reasons and competitive reasons. So there's the earlier SQL standards from 89, I think. Then there's a 92 standard, a 99 standard, and the vendors, although they contributed to the standards, have felt free to pick and choose which bits of the standards they'll implement, and as well as that, what they will add as their own proprietary extensions. And then they'll have a big battle in the standards committees to say, my particular extension is the one you should standardize on. But of course, in the real world, you've got customers who've used your extension and aren't going to go and rewrite everything they've done just because the standards committee had a battle and someone else won. So that's why there's so much variety. But there really is a core language with sort of extensions around the side of it. The full SQL has 3 bits we've talked about before: the DDL, the DML, and the DCL. The DML lets you insert, delete, modify, and query, retrieve data in the database. What we're interested in today is just that retrieval bit. We use the word query. A SQL query is the complete SQL statement that we drop into our SQL engine, and it comes back out with a table. So that's what we call a query. A query consists of a number of parts, a number of clauses. The first one is select, where we say what columns or expressions do we want to have returned from the query. Looks very much like a relational algebra select. We say which tables should this select work over. If you have more than one, it looks very much like a Cartesian product. The where, saying here's a set of conditions I want you to use to narrow down what data gets returned. That looks a lot like a projection expression. We'll skip group by and having for this week. And order by saying, when you return the results, please put them in this order for me. Please return the students' names in alphabetical order, for example. Just like relational algebra expressions returned a relation, an SQL query returns a table. And just as you can nest relational algebra expressions, you can nest SQL queries. You can say, select where, and then have another select statement inside the where clause, where the where clause will then go and evaluate an SQL query and return a set of tuples that you then use in your where clause. So you can nest queries just like you can nest expressions. And because these things are relations, they can contain duplicates, particularly the result tables may often contain duplicates, and we have special syntax saying how to handle those duplicates. Next slide. So, straightforward, ordinary SQL queries. SQL queries can be incredibly complex and arcane. Your brain can hurt when you're trying to work out what they do or how to write something. But the basic stuff is really straightforward. So we have this basic model, select from where. That's the basic model of an SQL query. So select name from student. It says, I want to get just the name field from all the student records. It's going to return a table with just the names. That looks very much like a projection, because it is. I can do magic thing of star. So if I don't want to name a particular, if I don't want to actually do a projection, I'll give me all the attributes. I can just put star in there. So that says this is effectively just returning student. Complete all the attributes, all the columns, all the rows from student. Select the names of all the Australian students. Now here we've got a where. So select from where country equals AU. This is our selection operation. That's our projection operation. General form is that. When we do one or more, that's going to be our Cartesian product. So a simple SFW query corresponds to that relational algebra expression in general. Selects the projection, even though the word is select and it maps onto projection, and where is called where but maps onto selection. That's just the way it is. You won't get confused after a little while. So a simple SFW query is exactly equivalent to that relational algebra expression for those of you who are interested in such things. So that little relational expression there is that SQL query. Now, I prefer to read that than that personally because the nesting is harder for me to understand. And SQL gets hard enough at times. So, some warnings, etc. SQL is a case-insensitive language. It doesn't care whether you spell select in uppercase, mixed case, or lowercase. It doesn't care. The same with all the table names and the attributes. They're all case-insensitive, which is good. If you're a Unix program, you may think that's horrible, but in most languages, that's pretty good. Quotes. The quote symbol in string constants in SQL is a single quote. That's good. Double quotes, you'll get syntax errors. You may look at them for a while working out what's wrong. The answer is you need a single quote. String constants are, of course, case sensitive. AUS is different to AUS. If you really want to do a string comparison that was case insensitive, there is syntax for that. But if I say if country equals AUS, I have to say that or that. And that's the way it is. Be really careful, as some of you will have found out already. Word processors and things like PowerPoint, a lot of tools designed to let you do formatted documents do a thing called smart quotes, where if I type quote, text, quote, it says, you're writing ordinary English, therefore I will be nice to you and do opening quote and closing quote. because on your computer keyboard you don't have opening quote symbol, closing quote symbol. So it does that for you. That Unicode character representing that lovely little curly quote symbol is not the same Unicode character as that simple quote character. So if you cut and paste something looking like that from an example from a textbook or possibly a Word document that someone's typed up as documentation, you may well get these quotes and then a really bizarre syntax error because it's looking for these types of quotes. And when I'm teaching some of these courses, students are doing copy and pasting all the time because we want them to, and they're constantly running into this problem. And when we're doing the course material, we have to be very careful about those quotes, but we won't get it always. In fact, when I was revising these lectures for tonight, one of the things I had to do was go and fix up all those quotes. I said by default, we get duplicates when we do a query. So if I say select country from student, I get this little relation. I've got Australia, Korea, Great Britain, China, Germany, and I've got 2 Australia in there. So that particular relation has duplicates, and that's the default. So I've got a magic keyword called distinct, which says get rid of the duplicates. So if I say select distinct country from student, it gets rid of the duplicate Australia and only get one copy of Australia. So I'll commonly do distinct as well in a query when that's what I want. But I know something could happen. These select statement can also have expressions in it. They can also have renames, which I'll come across later. And so here, pick up these fields from unit of study, but don't return the credit point value. Return a number which is twice the credit point number, because that's what I want, because I'm mapping into some other data structure or some other program where I expect that to be the case. Or for a practical example, I might have a number which is in dollars and cents with a decimal point in it, and I want to return a whole number of cents. So I could say amount star 100, and that would convert from a decimal number of dollars and cents to a number of complete cents. So there are lots of reasons why I might want to do that type of arithmetic in there. Where clause takes Boolean expressions, all the normal compare operations, except we have both not equals is both the greater, is a less than greater than pairing, or not equals. It gives you both choices because it's just trying to be nice to programmers who can't remember which particular convention this one uses, because some languages use that, some use this, and just gets confusing. And ands and ors, all the normal stuff. So here's an example. So select the units, just the UOS codes from unit of study, where the lecturer is 1001 and the credit points are at least greater than 4. String operations, conventional string operations are exact comparisons. There's a like operator, which you'll see I use later on in my big example, where I can say this thing is like this. This is now a string pattern, and there's 2 special characters in it, which are percent meaning anything and underscore meaning a single wildcard. That's a card character. That's often the equivalent of percent in other wildcard conventions, and that's the equivalent of a question mark or a dot. These things vary a lot from regular expression syntax to another. And there's other string operations as well. There's also a set of regular expression operators, but we're not going to cover them here. This is basic string operations. Rename. This is the equivalent of row that we had before, and this is really useful. So if I won't bother going back, it's too hard, but I said I did expression, I said credit times 2. I might want to call that something like double credit. So I could say credit star 2 as double credit. And then in my table I get back, that attribute will be called double credit. If I do this particular query here, then when I get my table back, this generates a table, that the schema for that table will have a student ID, an EMP ID, column called lecturer, and a mark table. That's cool. The last of those 4 things we have was order by. Great. Here's a table. Sort the rows of the table by this column. And I can sort them ascending, which is the default. So I don't say ascending, I get ascending by default. And descending, which means they're in descending order. And I can have multiple orders. So order by country and then name. That's fine. As complex as you want there. Right, so that's all the basic queries. Now we go on to the ones based on Cartesian products. Because all we could do so far is take a database, and we had this relational model, and we had lots of entities and had relationships. I haven't talked about relationships yet. This is where relationships come in. This is where we take one table and follow the links, the foreign keys, to other tables, and we do that with joins. So the way we navigate, the way we take a complex relational model and follow all those links and give us a query over multiple tables is with joins. The tables we're going to be joining together are specified in the from clause. You can think, if you want to, that what we do by specifying multiple tables in a from clause is a Cartesian product. And this example here, select star from student, unit of study, will give you just that. It'll do a Cartesian product of student and unit of study, which would basically be a totally useless query, because we're not in any way saying only the students doing that unit of study, which might be what you want to say. But when we put a where clause in, then we can now start linking these two things together on certain key attributes. And we specify the join predicate, the expressions which say this student value and this unit of study value are joined together by this expression. That's what we put in the join predicate in the where clause. So here we say student and enrolled. This is take all the students and their enrolled records and only give me those ones back where the student and the enrolled record are paired together via the student ID, and the unit of study code is info 2120. So now the result of doing this last, the from and the where, is I have all the students, a table with all the students doing info 2120, and its schema would be the Cartesian product schema, student and enrolled. But I don't want the Cartesian product schema. I just want student ID, name and gender. So I'll do that select clause on that. So this will just give me the student ID, name and gender of all students enrolled in 2120. So now I'm taking student and using the SID and tracing that up to enrolled, and SID, in enrolled, SID is the foreign key of a student. So magic will happen and I'll join those two things together. And when I do a from clause, like the one in the middle of the screen here, I can name things. So I can say from lecturer L and another copy of the lecturer table called M. So I'm doing from and from, but I'm giving the two copies separate names. There are two reasons why I want to do these aliases. One, because I may need to refer to something twice, like I'm doing here, or the other, just to save me typing. Because when I do the select clause, I can just give the name of an attribute. The name of the attribute is distinct. So there's nothing else has a name attribute, none of the other things in the from clause have a name attribute, that's fine. if I have the same named attribute in multiple tables in the from clause, then I have to distinguish them by saying lecturer.name. And that gets really boring after a while, typing the names of all the relations in the select clause. So I would often just put them in the from clause and then just use the abbreviations in the select clause and the where clause. But if I need to have the same table in the from clause twice, I can label them. So here I know which manager I'm talking, when I say L.manager, I know I mean this table, and M.empid, this table. I've got two copies of lecture. They're not really copies, but you can think of them that way. Two different roles. And we'll see me using the aliasing in the examples later on as well. So, what students are enrolled in what semester? We want SID, SName, and now semester. Yeah, I could say student.sid, which would take it from the student. Enrolled also has a student ID, but I know that because SID equals ESID, that they're the same. So I could choose either of those. I'll choose SID because it's cleaner. So student ID, student name, and the semester from the join, and I label them there. So here and here, except I haven't got to the verbose. And that, of course, is equivalent to a lovely relational algebra expression. And if any of you prefer that to that, that's very interesting, but I prefer this form. And I think we've talked about that. So this join is effectively a Cartesian product, which is the from clause, the selection, which is the where clause, and the final projections, which is the select. And that ordering can be important because we always do the Cartesian product logically before we do the selections. And this is theoretically what a join means, but of course not what it actually does. So by the time we take this and we drop it into, we parse it and get expression trees and optimize it, then doing a Cartesian product is always a very dumb thing to do, and they never do a Cartesian product. They work out exactly which rows they need to join to which other rows using indexes over the keys, etc., and give you the optimal result. Okay, there's a sort of somewhat tricky quiz question. So we've got distinct R to A, so all the distinct A's, where from RS and T, the A in R matches the A in S, or the A in R matches the A in T. And you might think you know what that does. You think we're trying to do this intersection, but we said earlier that the Cartesian product, if any of these is null, the Cartesian product will be null. So that's why one of the reasons why it's important to know that there really is a Cartesian product involved there. So you might think, oh, it doesn't matter if T is null because we'll just pick up these, the R's where we'll just pick up this intersection here. But if T is null, the whole thing goes to null because that expression may not force the null, but the Cartesian product will. Okay, the join menagerie. The stuff I just talked about is doing a join, and the join is implicit. So by the very fact that I put multiple tables in the for clause, in the from clause, and then put the where in, that is forcing a join. And that's an implicit join. It's actually an inner join, but in one of the standardization efforts, some people got carried away with joins And there's also explicit join syntax in SQL. The ones we just talked about are inner joins, and so there are a number of joins. And we'll do some of these in the tube. I use these occasionally. I particularly would use them if I actually wanted the semantics of them. So these were added. These, I don't think these were all in the very first SQL. They got added though for completeness. Once you start adding one type of fancy join, you have to add them all for completeness. So there's a general theta join, there's an equijoin, a natural join. You've seen what they mean before. And then these new ones are the outer joins, where when we've got something and we're joining with something and we don't match them, what do? In the inner join, we throw away the non-matching. We've got R and S, and some row in R has no match in S. What do? Do we throw it away, or do we create a new row in the product which has nulls for those? And that's what the outer joins are doing. Do we want to keep them or not? Okay. Lots of syntax there. So in a join, we're selecting all the students. We're taking a student, joining them with enroll, and we're joining them on student ID. So we've taken the student table, the enroll table, joined them, and we joined them on the SID. You can work out how we do that if we didn't use the join syntax as well. Now we're doing a natural left outer join, and go back to the data we had at the very beginning of this section. I said this is what we're basing everything on. You'd find student 210 didn't have any UOS codes defined. So in this case, we would have thrown them away. Here we keep them, and we put substitute nulls instead, because we're doing an outer join. Okay, getting close to finishing. Just like it, relational algebra has sets. SQL has set operations. I use these occasionally. When we do more complex SQL next week, I'll give you some examples of mine that do some of the more complex things like nested queries and set operations. These are quite useful at times. And because these are set operations, we get rid of duplicates automatically. So the first step is to remove duplicates from the tables, then do the set operations. Then normal set operations we've had union, intersect, and accept. Union, intersect, and accept. Boom, boom, boom. And if we want to keep duplicates rather than throwing them away, there's a magic word or and there's lots of practice on that in the tube this week. So let's do some practical examples. So we want to find all customers that have a loan, an account, or both. So we're now taking two select statements. Select statements return tables, and we can union tables. And this is a way of composing statements. So if you're writing code or you're typing SQL statements at a console, you type the statement, you hit return, or you say submit the query, and it returns a table to you. If you're running it interactively, it will type out the table. If you're running it from a program, you've now got some type of data structure which represents the table. But I can, inside the query engine, do a select, get a temporary table, and then do another select, get another table, and join them together. So that does that. Here's the customer names, customers that have an account, they're depositors, the customers who have loans, and I union those, and I'll now have a set of customer names who have either a loan or an account or both. If I want just the ones that have loans and accounts, the intersect gives me those. If I want to find just those who have an account and no loan, I'll find all the account customers and take away from that the ones who have loans, the borrowers. Quite useful. And it's very similar with the students who are enrolled in either of these courses, set of students, and in both of them, I do the intersection. And one of the things that actually makes marking and tutorials and quizzes harder in this type of course, there is often no right answer. There are many equally correct and good answers. If I was to ask you, find the students who are enrolled in either of those two courses, you would be perfectly allowed to submit that as an answer and that as an answer. They're both correct answers. You might think one's preferable because it's easier to read, but they're both correct. So SQL is one of these things where many correct answers are possible. The same with the database design. You can make arguments about lots of things there. So there are many things which are, some might be more correct than others, but they're often multiple good enough answers. So get back up slightly. So that's all cool. So we do that, we do that. Now we want to say students who are enrolled in both 5138 and 5418. Well, you think, oh, it's just the same as this. I want to know both. In the previous slide, I did a both with an intersect. Great. Oops. I don't know how to get back to that. Wrong key on the keyboard. Sorry about that. It's really embarrassing doing that when you're giving a public presentation and you click the mouse button wrongly and a mouse you've never used before, and all of a sudden you're 5 slides out with the audience staring at you. And a very, very strict timeline. You're wasting time. We're almost there. Very close. There we go. So you think, cool. So there's that one. And you think, oh, well, that's very similar. No, we just want to find in both. So that's a set operation. So we just take the intersection of the two circles. And that's fine. But this one is not equivalent to that. Because if that works, but this one, if we were to write that way, this is looking for enrolled records with two different values for the same attribute. No UOS code will be both that and that. So this will return nothing but that. So this is the only correct way of writing this. And that's the straightforward modification of something which is correct here. So this has got two correct ways of writing it. This only has one. Okay. Oh, I'm making really good time today. In terms of not having a lecture theatre full of students. Okay. So, in the very first lecture, I think I put up this. This is a lovely biological example of where genes are located in one particular organism and who it shares them with and what they are. And I said, this is the result of a single SQL query. What I did was I had a magic database and I ran a query over it, a single query, and that gave me a table. I took that table, dropped it into Excel, and then did an XY plot in Excel of bits of that table and That's what I got. And then I just annotated that Excel graph. That is the actual query that I used to do that. Now, when I put that up a couple of weeks ago, there were gasps about, it looks horribly complex. Everything that's in that query, we have covered tonight. It's a simple select from, where, order by query. So, and last week, I showed you the schema for this database. So let's look here. We've got species, which describes an organism. The genes, which are the set of annotated genes, where they are in the genome, what function they have, etc., for a particular species. This is the result of me cross-comparing. There's a long, complicated loading process where I take things and cross-compare them and generate a metric which says how similar one gene is to another. So I've done that as a background computation. And I'm going to take one species as a source organism, which is the, I'll go back to here, that's this guy, Acinetobacter baumannii, and that is that y-axis. The y-axis position in that source genome, and the x-axis is the number of a target. So I've got one species is a source and one species is a target. So I've got a species, which is my source, and a species, which is my target. As we talked about, I rename them, I give them a label so that I can distinguish the source and the target in all the complication, the select clause and the where clause. I've equally got two sets of genes. These are the genes from the target, from the source. These are the genes from the target. And I also want to know what type of structure these genes in the target come from, whether they come from the main genome or little ancillary genomes, and I can find that out from the sequences record. And I've also got another database, not this database, but another one, which has taxonomy, which says this organism is one of these, is one of these, is one of these. So that's a specialized taxonomy database. So I'm also going to take another database and link it into the same query as well. So I've got two databases, and in that first database, I've got the species twice, the genes twice. Gene-to-gene matches are from a source to a target, so I don't need to do anything fancy there, and then with my target. So that's a pretty straightforward from clause. I've got a select clause, which just says bits and pieces of all the results of this. In here, I've got expressions. So one of the fields in the gene record is a thing called a cog, just the name of it. And that's a little code. And I only want the first 7 characters of that string, because after that, there's some other stuff which I don't want. So I'm doing a substring operation expression in here, and I'm relabeling that expression in the result table as cog. And then I'm taking, that's the first 7 characters. The 8th character is a magic type, which is really useful to me, and I'm going to call that cog type. And I'm going to create a blank column called cog fun, because later on in my post-processing, I'm going to want to do some complex stuff and fill in a function there as well. And various bits. There's another nice expression. How many matches were there? That's a percentage, so I multiply it by 100 and divide it by the length of the thing. That gives me a percentage again. And I call that matches. Good. So I do that. So now I've labeled all the columns. I've selected which output columns I want and relabeled them appropriately. And here's this straightforward expression which says which ones I'm interested in. I'm using the from, where type joining. So there's lots of joins in here. So that clause there, ooh, careful about doing that. That clause there, the GH target species number equals T.spark target species number, is forcing a join between a GH tuple and a species number, and a target species tuple. So a lot of those, here we've got a mixture of join type expressions and basically sort of selection type ones. So I'm only interested in my source target being that particular organism. So that's a straightforward selection expression. That's a join expression. Inside my source, I'm only interested in a particular region. So that's effectively a selection expression. More joins, and this is a selection because I'm only interested in this query on things which give me this degree of matching. If it's less than some threshold, don't care. And here's some things I'm throwing out. So this whole bit towards the end here, that whole second half of it is just selection being used to throw out non-interesting rows which are boring stuff, transposases and etc., things which are really common and they're just noise. And I don't want to pick up close relatives, so if I've got other Acinetobacters, throw them out as well. So the first half is primarily selection plus some joins, and the second half is all just winnowing away stuff I'm not interested in, and then I follow it by an order saying, here's the order I want my final table. So it may look sort of scary, but it's really very simple. I could have rewritten it using the join syntax, but I didn't because that's not what I did. They're effectively equivalent, in which case some of these would have had join syntax and some of them wouldn't have, but I didn't write it that way. When we see some queries next week, I might put some joins in as an example. Okay, references for this week, the normal textbook, some nice discussions inside the textbooks as well. Okay, so by now, you should be able to do basic SQL queries, and you should be able to do basic join operations. And if you think about it hard, you should be able to do some of the fancier joins as well. And you should be able to do set operations, and you should understand why SQL is underpinned by relational algebra. And if you really wanted to, you could write relational algebra expressions that corresponded to SQL queries. In this week's tute, questions that's the type of thing you do. In this week's quiz, you've also got a lot of RA practice. Next week, we'll do more advanced SQL, nested queries, aggregation, grouping, handling nulls, and other complexities. And we'll move on from there. And we've got some spare slides, which are here just in case we finished early, which might as well go through. And you saw that this between operator in that complicated example. So if I wanted to find all students ordered by, wanted to find all student IDs, not student names, but just the list of student IDs, again, distinctions or high distinctions in Comp 5138. Now we don't have a grade in the assessment table, but we do have a mark. And if we had a grade, we could say where US code equals 5138 and grade equals, bracket grade equals D or grade equals HD. But as we've got a mark, and we know that D cutoff is 75 and HD cutoff at the top end is 100, so we can say and mark between 75 and 100, and that will give us that's between. And if when I did the, go back to here, oops, go back to here actually, See this x-axis is between, the y-axis is between 260,000 and 330,000, because that happened to be the region of that organism that I knew had these interesting genes in it. And I go to that particular where clause there, and I say, only look at genes between here and here. So there's an example in that query of the between clause. Okay, so there's some more examples. It should all be pretty straightforward. Oh, there's an in clause there, more fancy syntax. I talked briefly about string expressions and the like statement. Speaking of like, there's some likes in here. There we go. Gene product not like something containing transpose. I don't care what's in front of it, I don't care what's after it, but it's got the word transpose in it. So I'm going to exclude things that look like transpose. And in the biology are things called transposases, and I'm not interested in them. So there's transposons and there's lots of various transposon-y words, but they've all got transpose in it. So, and the same, all these integrase things, there might be various versions of that, but I don't care about them. I want to throw them all out. So I'm just looking at a pattern which has that word in the middle of it. And the last thing on that previous slide was in. So I'm doing a substring operation, and I'm saying, and that magic function code that I called up here, that last character called cog type. And I said the cog type is not a J or an A or a K or an L or a B or a D. They're all really boring things. So I'm using an in clause there. Go back to here. There's in clauses as well. So when I talked about like, I said there are other things as well. There are also full regular expressions for those of you who are fascinated by regular expressions, the Perl programmers amongst us. And there are regular expressions in SQL. These are one of the things I would tread carefully and not necessarily expect them to be highly standardized, because they came in SQL Standard 2003, which is about the time all the wheels started falling off the standards. So very likely to be present in your SQL implementation, but not necessarily to be exactly the same syntax in all of them, but useful to have. There is date and time, and so yes, you can represent date and time, but you don't need to represent them as strings, varchars. You can represent them as dates and times. And SQL knows about dates and times, and it has semantic operations on them. Just like Excel knows about dates. You can add one to a date. I could have that date, and I can add 1 to it, or add 7 to it, and it will be the correct calendar date because it knows about dates. I can take times and subtract time from another time and get a time interval. So these are fully fledged data types in their own right. And all the normal operations work on it. That's cool. And there's some constants. Again, these are things, before I use them, I would just check up on my implementation that I'm using exactly what the syntax is. Of course, they are semi-standardized. And their operations, of course, to pull them apart and create them, etc. So there's an operation to say, how do I initialize a date? Well, I can't store a string inside a date field because it's a date field, not a string. So in this particular syntax, I say date, the magic word date, followed by a text string, which is the date. And that will convert that text string into the corresponding date. but check it up on your system. This is likely to be different. And that really is the last of the slides for that week, and it's 10:02. That's a pretty good time.